Good afternoon. We are going to do one more motion problem, and this one was from the 2019 exam as well. And I like this problem because they're so clever, these AP writers, because they combined not only a motion problem but then the table, right? And then you'll see some other stuff in here that they embedded. It's just amazing. So at first you go, oh, it's a table problem, but then you start looking, you start reading, and it's like, oh, the velocity of the particle. Okay, this is actually a motion problem with the table giving us some information. So we're moving along the x-axis given by the differential function, okay, v of p, where v of p is measured in meters per hour. All right, and t is measured in hours. Selected values of v of p are shown in the table above. The particle p is at the origin at time t equals 0. So just glancing at the table, we know we're moving. Yeah, we're moving right, and then we move left, and then we go right again. Yeah, because our velocities are positive, except for right there. Okay, so we already know some stuff. All right, now they're going to ask us justify why there must be at least one time t from 0.3 to 2.8 at which v prime of t, the acceleration of the particle, equals 0 meters per hour per hour. Okay, so they told us because v of p is differentiable, what do we know applies? What theorem applies here? You got it. MVT, right? The mean value theorem. And you see something here, right? 55 and 55. So we can say, okay, so we can say v prime of t is equal to, approximately equal to, right? Approximately equal to Vp of 2.8 minus Vp of 0.3 all over 2.8 minus 0.3. And then we can say, okay, that's equal to 55 minus 55 over 2.5, which is 0 meters per hour squared. Okay, so if this is true, MVT, or mean value theorem, guarantees at least one value C on this interval 0.3 to 2.8 where v prime of p of c is equal to 0. And you can stop there. Okay, so that's A. Okay. And MVT is your justification. You are going to get a point for that. All right. My husband's talking too loud, working from home, right? Okay, here we go. Now, the part B, now use a trapezoidal sum on 3 intervals. So this one's fairly straightforward. They're telling us exactly what to do, okay, to approximate the values. So we're going to say 0 to 2.8, Vp of t, dt is approximately equal to, right, our trapezoidal sum. Now remember the trapezoid is the width over 2, so 0.3 over 2 times the sum of the bases, and the bases are the height of the function here. So 0 plus 55 plus, we're going to add that to the next one here, 1.7 minus 0.3. Let's just do these here and you guys can get that idea, would be 1.4, right? And then 2.8 minus 1.7 is 1.1. And the we're only doing 3 though. 1.7. Oh, and then we're stopping. Okay. All right, so 1.4 divided by 2. 55 plus a negative 29, and then plus 1.1 over 2 negative 29 plus 55. And we plug that all into our calculator. I think we do need to calculate it. And let's see what we get. So 0.3 by 2 equals times 55. So I got 8. I'm going to just put these numbers up above. 8.25 plus 1.4 divided by 2 is 0.7 times 55. Oops. So 18.2 there, and the last one times 1.1 divided by 2, and 14.3. And we add all those up. I got 40.75. Now what is that? What is that? What is that? We anti-derived velocity. So we get, yes, you got it, position. So that would be meters. Okay, that's how far the particle P went, right? Okay, so part C, you guys want to see that? I'm going to fold my paper down so you can see this better. Okay, and do part C. There you go. Okay. A second particle Q also moves along the x-axis so that its velocity for 0 to 4 is given by this equation. Ooh, that's a nasty one, isn't it? Meters per hour. Find the time interval during which the velocity of the particle Q is at least 60 meters per hour. Find the distance traveled by the particle Q during the interval when the velocity of the particle, is at least 60 meters per hour. Okay, so I'm going to put this into my calculator. So I'm going to clear out the y's here, and I'm going to put this in. So 45 times the square root of x cosine 0.063 x squared. Okay, boy, that looks like fun, doesn't it? Okay, and we also want to know where it's greater than 60. So I'm going to put my y2 as 60. Hope that makes sense to everybody. There we go. Now you can see it. All right, and then we're going to graph, and I'm not sure our window is going to be 0 to 4, right? And I'm not sure what. I have 0 to 50, but it needs to be greater than 60, so I'm going to make this like 100. I don't even know. We'll see what that looks like. Oh, look at that. That looks beautiful. Okay, so here you can definitely see this is 60 meters per hour. So from here to here, we are greater than 60 meters per hour. So we need to find those points. So second function calc, intersect, and enter, enter, enter. And it clicks right on there. So we're going to say at t is equal to 1.866. I'm just going to truncate it, and then t is equal to, now we have to find the other one. Second function calc 5 intersect function. Now we have to scroll over there. Let's scroll. So you need to get kind of near it and then enter, and it'll grab the other one. So it's 3.5191. We'll just truncate it at 4 decimal places. Okay. Now it says, find the distance traveled. How do we find the distance traveled? You're absolutely right. Anti-derived velocity, we get position. You got it. So let's go ahead and do that. We are going to anti-derive velocity from 1.8611. Ooh, no, 661, sorry, to 3.5191. And we are going to do VQ of t dt, and that is going to be the distance traveled by particle Q during this interval. And we could say T1 and T2. That might be kind of nice. Okay, so we're going to quit out of there, and we are going to math. You remembered 9, yes. And we're going to plug in 1.8661 to 3.5191. And remember, it was our Y1 that had that. We already plugged that in. So remember, alpha F4 gets us Y1, and our variable is X. And we enter that, and we get 106.1091. And so that is, we anti-drive velocity, we get position, so that's in meters. Okay, that was part C. Now finally part D. Can you see it? Yes, you can. All right. At time t equals 0, particle Q is at a position of -90. Okay, they're giving us an initial condition here. Now, using the result from part B, okay, that's about particle P, right? And the function VQ from part C, approximate the distance between the particles at t equals 2.8. Okay, so we're going to go back here to part B. We're going to look at this. Okay, so we have 40.75 meters from 0 to 2.8. And they said, so if we integrate 0 to 2.8, V of P, sorry about that, I messed up, T dt, sorry about that. Okay, that's a little bit messy. If we anti-drive velocity, we get position, right? So this is the position at 2.8 minus the position at 0. Well, we found this already, right, guys? We found that was 40.75 meters. And they told us at 0, this is key, particle P is at the origin at time t equals 0. So this is 0. So this is our location, okay? So that's important. Okay, now we're going to go back. So we found the position for particle P. Now we have to find the position for particle Q. And we're going to go, again, we're going to anti-derive from what we know to what we want to know. So now we're going to do from 0 to 2.8 V of Q T dt. And that's going to give us the position at Q at 2.8, top minus bottom, right? Position of Q at 0. Okay, this time the position of Q at 0 is -90. This is what we're looking for. And this we can figure out on the calculator. So we can do this really snappy. So again, we'll do math 9 from 0 to 2.8. And we already have this plugged in as Y1. So alpha F4, I always have to remember that. And X. You guys see that? Yeah. Okay. And it's thinking. I'm going to write calculator here. And this is from part B. Okay, so you'll notice sometimes they have us do the integral using a trapezoidal approximation. Sometimes they have the integral using the calculator. Sometimes they have the integral using a graph, right? The area under the curve. So sometimes you'll see it all different ways. Okay, and then subtracting a -90 is like adding 90, right? So then we have to subtract it over. of Q of 2.8. Can you guys see that still? Not quite. Let's move you up. There we go. Okay. So 135.937 minus 90 gives us 45. 45.937 meters. And so let's go back to the question, see what they're asking. So approximate the distance between the particles Q and particle P. Okay, so now we just have to subtract the two. So Q minus x of P, so it's 45.937 minus 40.75. And we get approximately 5.187 meters apart. We could say apart. I don't know how they would want us to say that, but there we go. We're done. One more motion problem combined with the table, which is kind of fun. Thanks, guys.